Now that we've laid a foundation and understand a bit more about tangent lines and how to build formulas for them, we can use that to answer some interesting geometric problems, little puzzles like the one that follows. We're asked here to find the equations of all the lines through the origin that are also tangent to the parabola given here. The key thing we're going to need for this is that we're talking about tangent lines. That's the same, or will have the same formula as the linear approximations that we've seen previously. In this kind of problem, having a sketch, especially one that we can label with some details, can really help. So here's a rough sketch of a parabola that opens upwards. It's been shifted away from the origin. And what we're interested in are the points where the lines through the origin are also tangent to the parabola. So we can imagine right here, there might be a point here where that happens, but it's not going to be every point. For example, if we pick this point on the parabola and drew a tangent line there, it definitely is not going through the origin. It's shooting off to other places. Likewise, if we drew a tangent line at that location, it's also not going to go through the origin. So what we'd expect to see is maybe two different points. So we might see, it looks like 2 points, maybe 1 point, where the tangent line goes through the origin. Now, how are we going to actually solve for those locations? What makes them special? Well, we're going to need a few different things, and let's just draw one of these as a hypothetical. Let's consider this point here. It'll be special. Let's say we're looking for that point, and based on the nomenclature of our earlier formulas, let's call that point x equals a, but a is the x value. We're going to need to keep x free, and this is where it can get a bit confusing for some students. We're going to need to keep x free because we want the equation of this line. Equation of the tangent line. Well, we know how this equation works. It's y equals the slope. And here you have to be very careful about the x's versus the a's. If we pick a point A and we draw the tangent line, that's the a value that goes into our slope calculation. Then we multiply that times x minus a. That's another key ingredient here. This is the constant, and x is the point that we're considering along the line. So x is still a variable. And last but not least, plus f of a. So this is the equation of a tangent line based on the point x equals a on the parabola. Fair enough. In fact, that actually defines the green lines as well. If you picked a to be -3, say in the sketch, you would get the formula for this green line. If you picked 1, it might be this green line. So how does that help us? Well, we want the a's such that the line passes through the origin. And the origin specifically has the coordinate 0, 0. So A is the anchor point for the line, but what we want to guarantee is that x equals 0, y equals 0 satisfies the line equation. This is x changes as we go to left to right, and the y changes correspondingly. I want to know if I plug in x equals 0, will I also get a height of 0? That's not true in this line here. In this line, if we went to x equals 0, we would get a y that's positive. On this one, if we were to follow it all the way down where x equals 0, it would give us something massive and negative. So this is going to be a special condition on the line. And so we can plug that in. We want 0, copying this over, to equal f prime of a times x minus a plus f of a, and actually the x is also now a 0. All right. Well, this so far hasn't used the details of the parabola that we were given. Well, that's exactly what we have for f of a, and we can find out the value for f prime of a. So this function gives us the y values, or if you like, this whole thing here is f of x. And so what we can do is plug those values in. We'll do that on the next page with the 0 subbed in. If our function is this, then we can take the derivative and find the slope at any point. And once we've done those two calculations, or restated this formula and done the derivative calculation, then we can evaluate both of them at a, which is almost too simple substitution. we just replace all the x's with a's. And then we sub those into our tangent line formula, which satisfies 0, 0. And that was 0 equals our slope at a, 2a minus 2, times our coordinate x of 0 minus a, plus f of a, so a squared minus 2a plus 4. So going back to the picture, we wanted the point A where if we were to build a line, that's this formula here, it would satisfy 0, 0 as x and y coordinates on that line, and the height we would have for our A comes from the parabola, so we use the parabola formula there, and the slope we would use for that line comes from the derivative of the parabola to get the right slope. And this gives us an equation in A where the only variable left to solve for is that A, and when it pops out it should be the location on the parabola that we're looking for. So let's tidy this up and solve for A. We'll have 0 equals minus 2a squared plus 2a's plus an a squared minus 2a plus 4. Together this gives us negative a squared plus 4. That's nice because that gives us a squared equals 4, or a equals 2, and minus 2. And those would be the points on the parabola, specifically the x-coordinates, where the tangent line will pass through the origin. This is practically crying out for a visual representation to confirm our answer. We're going to do that on the next page. The parabola we're working with is restated here, and we can do a quick table of values to get a sketch of this. We know we want to go from around negative 2, certainly up to 2. Let's go up to 3 and see what happens. We plug in the coordinates and get the corresponding y values. We're going to get 12, 7, 4, then it'll be down to 3, then back up to 4, and there we go, we're actually back up to 7 for that. And if we draw that out on our axes here, everything's above 0, so we'll center our axes there, and we will sketch out our coordinates, x and y. There's exactly 12 steps in this grid, so if we use our scaling like so, and make this our 6 mark, then we can easily get the rest of the graph sketched in here. 4, 3, 4, and 7. Sketching that parabola. And now we take the 2 points that we found. Notice it's not symmetric around 0. That's fine. That wasn't quite what we were asked for. But if we go up to this point here and draw the tangent line, lo and behold, it looks like that tangent line does in fact pass through the origin. We draw the tangent line there, it ends up through the origin. Likewise, with a different slope, but still satisfying that same property, we can see that, at least to a rough sketch, the tangent line that passes through that point also goes through the origin. That is not the case for other points. If we were to pick this point and draw the tangent line very clearly, it does not go through the origin at all. It ends up over here somewhere. So these 2 points at x equals 2 and x equals minus 2, those tangent lines to the parabola pass through the origin. This is a little less convincing than the algebraic version, but it certainly gives us some reassurance that what we found for the algebra is correct.